All right, and set up from current slide. All right. All right. Okay, a quick review of where we are, where we're heading. We will be doing, hopefully getting pretty close to finishing chapter 6 today. If not, we'll be within striking distance on Tuesday. If we do finish today, then Tuesday we'll have the test on chapter 6. Y'all are asking about that. So we'll shoot for that. We've got a lab coming up this afternoon. Will look a lot like the last lab, but it's has some differences. So we'll do that. I don't think it'll take you all that long, but I'll allow you 2 hours for it. And then when you finish that, you will be free to go. And like I said, if we finish chapter 6 today, then Tuesday we will start chapter 8 and have the last lab in chapter 6 and then the test. If we don't finish chapter 6 today, we'll finish chapter 6 on Tuesday and have the last lab on Tuesday and then have the test the following Thursday. And then we'll get as far as we can in chapter 8 whenever we get to start it. And Josh is here. Well, let's see. I see what I did now. I marked Alexis in Josh's place, and now so I've already got him marked. Okay, good deal. And here's Tef. I know you're in. There you are. All right. So the question that was asked earlier, how many more tests? We'll have the chapter 6 test, and then we'll get going in chapter 8. We may or may not quite finish chapter 8, but we'll get far enough to have a test, and it's a pretty short and simple test. There's only one lab for chapter 8. We'll do that the very last day. Now remember, we have class today, next week, Tuesday and Thursday, and we have class the following Tuesday and the final on Thursday. That's how they do mini-term classes, second mini-term. It's not a week of finals, it's 1 day of class and 1 day of finals. In fact, the way they print it up, they say you have class both days, Tuesday and Thursday, and then have the final on Friday. I didn't think probably y'all were particularly wanting to do it that way, so we'll try to wrap everything up by Tuesday will be the last day of class, and then on Thursday we'll have our final exam. Okay, and Shanika is here. And did anyone else come in? I thought I saw somebody, but I guess not. Okay. So, any questions? How we're going to proceed or where we go? So, we have today's lab, one more lab on chapter 6, and then we'll have one lab on chapter 8. So, today's lab and 2 more labs is all we got. And test, chapter 6 test, chapter 8 test, and the final. Now, if it comes down to it, and it probably will, we'll still be doing chapter 8 stuff on that Tuesday of finals week. And then once we're finished with chapter 8, and we'll do the lab for chapter 8, then on the final exam day, you actually have 2 tests, chapter 8 test, and then the final exam. The final exam is comprehensive. The chapter 8 test is just as short as these others, so you'll be done in probably less than 30 minutes for that. And the final exam is even easier and shorter. So the odds are you'll be through with that in 15 minutes or so. So we'll have a lot of time on final exam day. Yeah?
Do you drop any grades in this class?
I will drop your lowest lab score and your lowest test score. Okay? Now, you have to have your paper turned in, or else you'll need all your test scores to bring up that 0.
Yeah, and the
right?
paper is due today, right?
No, actually next Tuesday. Yeah, okay. No, for some people today.
Yeah.
Okay, right. Okay, and I can tell you've been eating. Okay, so, all right. Any questions then? Where we've been, where we're going. All right. The first half approximately of this chapter was on electricity, and today's lab will be on electricity. The second half of the chapter is on magnetism, and so the last lab will be on electromagnetism. It has some electrical components, some magnetic, more magnetic, but we'll be doing that probably Tuesday if we finish it. Yeah, probably Tuesday, no matter what. All right, no questions? All right, let's say magnetism. We have known, meaning mankind, the human species, has known about magnetism far longer than we've known about electricity. And we've used magnetism way, way longer than we have used electricity. The earliest ideas, earliest discoveries about it, were known to be associated with naturally occurring magnetic materials. Now, the common name for this is lodestone. It's actually a mineral. The name of the mineral is magnetite that has magnetic characteristics. It attracts other magnetic materials, and it's naturally occurring magnet. The old name for it was lodestone. The current mineral name is magnetite. Now, magnetite is a special iron ore, and it has exactly the same composition as what they call hematite, which is iron ore. The only difference is hematite is not magnetic and magnetite is magnetic. Okay? Rather bizarre. Chemically, they're identical. It's just one's magnetic and the other is not. Okay? And before we get into how magnetite is magnetic and hematite not, we'll get to that in several slides, but we'll get there after a while. Magnets in general are characterized by poles. Who came up with the name poles, I'm not sure, except one pointed toward the North Pole and one pointed, of course, the other end pointed to the South Pole. So that's perhaps why they were named poles. Rather than calling them North Poles and South Poles, which we do, everybody does, the better name is the North-seeking pole and the South-seeking pole. Because from what we are going to say in another slide or two, we have a problem when we call them North and South Poles. We'll get there. Now, the only other, and like I said, this was iron, an iron ore that happens to be magnetic. The only other magnetic materials, naturally occurring magnetic materials, are iron, cobalt, and nickel. 3 metals. And if you happen to glance at a periodic table, and here's a periodic table, you will find them listed right here. There's iron, there's cobalt, and there's nickel. Not too surprising that they're right next to one another. And they're in one group called 8B. Over here is 7B, over here is 1B, this is your 8B. That's not too surprising either. Maybe a surprising thing is the things underneath it are not magnetic. But those 3 right in a row are the only 3 naturally occurring magnetic materials. And we call those the ferromagnetic materials. Where did we get the term ferro? Any ideas? Second? Egypt, okay. Probably more like Greek, but it could have been Egypt, I don't know. But what does that mean? Ferro. What's that associated with?
Pharaoh.
No, okay, I see what you were thinking. That's a PHAROAH, okay? Not a FERRO. Now I got it. It was kind of slow this afternoon. Okay. Well, when I just showed you the iron on the periodic table, did anyone notice its symbol? Fe, okay? Now, actually, that came from, at least my understanding is, that came from the fact that to purify iron, you put it through fire. So that ferro means fire, okay? But that's the symbol we use for iron. It's the name we have for iron. The 2 oxides, ferrous oxide and ferric oxide, they have that name in it, okay? So these are the iron-related magnetic materials. Iron, cobalt, and nickel. They go together. Now, iron is the most prevalent element in the earth. Notice I didn't say on the earth, in the earth. Almost our entire core is iron, okay? The molten core is mostly iron. The very, very deepest rocks we find is iron, okay? It's only the mined iron, which Birmingham, Bessemer are very famous for. Those are just places where the iron has made its way to the surface. If we could go deep enough, cheap enough, we'd have all the iron we wanted. But it's pretty expensive to go down there. But the whole vast majority of the Earth's mineral content is iron. One of the other major, maybe not number 2, but probably like number 3, is nickel. But again, it's mostly way deep in the earth. Some outcroppings on the surface, but not much. Cobalt seems to be pretty rare. I've never seen anyone or heard anyone talk about deposits of cobalt. But that must be fairly, it has to be common somewhere, because those 3 are our ferromagnetic materials. Okay? Now that was the earliest idea. That's what this kind of stuff we've known for decades. I mean centuries. Okay? The modern view. Magnetism is associated with magnetic fields. Now, just like we said before, if you have an electric charge, you've got an electric field. Okay? If that charge happens to be positive, which way is the field pointing? Electric fields always point away from a positive charge and toward a negative charge. Any charge you have has an electric field around it. Okay? Anytime you have a magnet, it's associated with a magnetic field. You can't see a field, you can't feel a field, you can't experience a field, but they're there. Okay? Now we can show evidence of a field. The field lines, and here's the convention for magnets. We say they go from the north poles and point toward the south poles. So the field lines always point away from north poles toward south poles. Just like electric field lines go away from positive charges toward negative charges. So there's a connection between magnetism and electricity. There's 2 different entities. Charges for electricity, poles for magnetism. Okay? Now, magnetic field, this is what I was just saying, magnetic fields and poles are inseparable. If you have a magnetic field, there's a pole somewhere around there. If you have a magnetic pole, there is a field around that. Now, here's one difference between electricity and magnetism. You can have an isolated positive charge out here, no sweat, or an isolated negative charge, no problem. You can have positive and negatives together, or they're usually not absolutely together, separated somewhere. However, no one has ever been able to isolate either a north pole or a south pole of a magnet, ever. Okay? Now they tried. Someone had a magnet, say a bar magnet, and said, well, let's cut it in 2. No, okay. Let's go back to the field lines. How you can represent field lines is put that bar magnet under a sheet of paper, thin sheet of paper, and sprinkle iron filings on it. Remember, iron, nickel, and cobalt are the only magnetic materials. Iron filings are pretty common. Sprinkle that on top, and you see they all line up according to those field lines. You can see pictures in the text. Okay? Now, if you notice that, just about all the filings will then go toward the poles. Okay? And they'll be sticking out all over. In the middle, hardly any filings go. They all gravitate toward the poles. Okay? So here we have North Pole, South Pole. And let's just cut it in 2 and isolate the North Pole. Will you do that? What do you get? You get 2 magnets. The North Pole, South Pole here, North Pole, South Pole there. All of a sudden, this middle that had no attraction for iron filings, as soon as you break it in 2, cut it in 2, or whatever, then you put it over here, all those filings there, with the sound effect, they're all there, okay? So you've just created new poles, 2 new poles, in fact, okay? The north, the south on this one, the north on that one. So you will never, ever be able to isolate either of the poles. They always come in north-south pairs. Always. Now, and as we already said, the field lines, the convention is they point away from the North Pole toward the South Pole. Now already we're saying North Pole and South Poles again, whereas the previous slide said we really should be saying north-seeking poles and south-seeking poles. We'll get into that reason in a minute. So, here is a rule, and it's a lot like you had for electricity. What did like charges do? Repelled each other. What did unlike charges do? Attracted each other, for sure. So what do like poles do? Repel each other, and unlike poles attract each other. It's very similar to electricity. Why am I making all these comparisons? In a very short while, probably later in this today, we'll get to how they're connected, and they are definitely connected. Okay, so like magnetic poles repel, unlike poles attract. And here is the picture illustrating what I was showing. You had a long magnet here. If you were to put filings here, they would all congregate here, nothing in the middle. Almost nothing. Okay? Break it in two somehow, and suddenly you've got a new South Pole and a new North Pole. Put filings on it. They're all over both of them. Whereas they weren't anywhere close to them in here. Break them again. Okay. You get them. You make a new North Pole and a new South Pole every time you break it. And that's why, I don't know if any of you have seen the little refrigerator magnets. All you needed was one long big magnet and just slice it as thin as you want to. You have North Pole, South Pole. I mean, it's amazing that they would be that strong. But you can't separate the two. They are always dipoles. Okay, we'll see that in the next lab, not today's lab. The one we do on electromagnetism. So here's the illustration of our field lines. They always point away from the North Pole and toward the South Pole. Now this is a two-dimensional illustration. If we could go behind the board, they would be doing that too. Always point out in every direction, pointing away from north and to the south. And if you'll notice, the field lines are concentrated here and concentrated there with basically almost no field lines here. That's what the iron filings were showing you. No field lines there. Okay? I don't know what was there, but nothing. Now, sources of magnetic field. Got to turn my page. Oh, in the text, there's a pretty good illustration here of a bar magnet. Looks like a pretty strong bar magnet. Been dropped or placed near iron filings. Look at that. No iron filings in the middle. They're all over the ends, three-dimensionally. Someone's wiped off the N and S so just you can see the letters there. But they would have been on top of that too. All right. So, let's talk about magnetic fields. We've already seen the illustration. Well, no, actually, we've already talked about magnetic fields. Now, we got something coming up here that is on page 157, but we haven't gotten to it in the text yet. So we'll get to it in the text, come back and see the figure in 157. So what are the sources of these magnetic fields? Well, like so many things, like chapter 4 when we did that, we were doing heat and energy, internal energy, that type of thing, heat and temperature. Those are macroscopic phenomena. We can measure, we can study, we can do all this stuff too, but all of it had the base at microscopic levels. What is going on the atomic level, the molecular level, the very, very small level that produces what we see and measure on the everyday scale level? Well, same thing here. We first look microscopically, and then we'll see what the results are macroscopically. Well, in these three elements only. Well, wait. Okay. Let's talk about general. Okay? In general. atom is made up of protons, neutrons located in the nucleus. Okay? Then you have around that electrons flying around, three-dimensional. Okay? All over the place. Okay? Now, the protons and neutrons, they probably are doing a lot of things in the nucleus, but it's so tiny, so compact, so dense, it's really hard for us to measure or tell what's going on in there. So we just let them do whatever they want to. The electrons, however, are in this huge cloud. When I say huge, space-wise huge, but the electrons have almost no mass at all. So it's not a huge mass, it's just a huge cloud. All that mass is concentrated in a tiny little pixel dot, and the rest of the space is occupied by almost nothing. Tiny, tiny, tiny little electrons. So it's what these electrons are doing that basically give a lot of things their character. Justin just couldn't pull himself away from all those desserts, I can tell. Okay. They had desserts out at the building construction place, and I talk about good desserts. I could hardly pull myself away from them. Okay. That's part of L Day, by the way. Okay, so what's happening with those electrons? Well, two things are happening. Okay? It says protons too, but we're not really going to worry about those so much. Let's look at the electrons. Okay? One thing the electrons are doing are spinning. Okay? In fact, we are going to get to it in the chapter 8, talking about the quantum numbers, and the last quantum number we'll look at will be the spin quantum number. Electrons spin either up or down. Okay? So we'll get there later. So that's one thing these do. Now I'm sure the protons spin too, but I don't think it affects anything we can measure. I'm not sure on that, but I don't think so. The other thing electrons are doing are going around the nucleus, right? Just all over around there. Now, generally, for any electron doing this around the nucleus, there's another one doing this, one doing this, one doing, they're just all over the place. So usually there is no, what we call net effect of that, except in iron, nickel, and cobalt. Those are the only three. There's something about the way those electrons move around the nuclei or spin around the nuclei that give it the magnetic field. Okay? Something bizarre there. Now, because of that, let me just say this. The way they've organized this on the slide set is rather bizarre. We'll come back and see pictures of what we're talking about here in just a minute. But the macroscopic effect fields that we see are either in permanent magnets, we'll see it in Earth's magnetic field, we'll see it in electric currents themselves, and we'll see it in electromagnets. Okay? The macroscopic fields we'll see in all four of those situations. So let's see permanent magnets first. Now we see what's going on. Okay. To make a magnet, to have a magnet, to be magnetic, to be attracted to a magnet, anything to do with magnetism, you got to be one of those three ferromagnetic materials. Iron, nickel, or cobalt, or some combination of them, or alloy of them. Okay? Only ones you have. And just by the way, the iron magnets are what they call soft magnets. Doesn't mean iron is soft. It's anything but soft. But it means the magnetic characteristics are, it's easy to magnetize iron materials, but it's also easy for those iron materials to lose their magnetism. Okay? Whereas nickel, they're very hard to magnetize, but then once you have them, they're hard to lose the magnetism. So they're called hard magnetic material. Iron's called soft, and cobalt is somewhere in between, but we just don't have that much cobalt anyway, so we don't really worry about this. So there's something about those three materials, iron, nickel, and cobalt, about their atomic magnetic moment. Okay? And this comes from two things, and they list proton here too. the electron-proton intrinsic moments, okay, that's coming from their spins. And again, I can't wrap my head around how a proton spin is going to influence this, but maybe it does. The other is the electron orbital motion. And maybe it's a combination of the two, I don't know, but these three materials are the only three that will produce an atomic moment, a magnetic moment at the atomic level. So every atom of iron, nickel, and cobalt is a little magnet, okay? Something about the spin of the electrons or the orbit of the electrons or something makes it a little magnet, okay? Now, remember that hematite I talked about, the naturally occurring iron ore that was not magnetic? Well, in that, every one of those atoms is magnetic. But then they'll be like this and this and this and this, all mixed up, and so they don't have any naturally occurring magnetic field. Okay? Well, actually what happens, they cluster together in what they call domains. And those clusters of atomic domains, they can be pointing in all sorts of directions. Now, this is only two-dimensional. They could be three-dimensional, pointing all sorts of ways, otherwise not magnetic. Pure iron, every atom of that iron, or nickel, or cobalt, has a magnetic moment, would be a little magnet, but they're randomly distributed in here, so they don't have an overall. They're demagnetized. Okay? Not magnetized. Domains are randomly oriented. Now, if you take this piece of metal, randomly oriented domains, and stick it in a strong magnetic field, or maybe even not all that strong, you're going to align several of those to point along the magnetic field. Remember, the magnetic field lines point away from north toward the south, okay? And then you'll have these typically aligning up. Not all, but many of them aligning up that way, so this then becomes magnetized, okay? So this will be magnetized. Now we're going to see how this happens and the result of this a little bit later, okay? When they are not magnetized, the domains are randomly oriented. When they are, they're more aligned with some sort of magnetic field. And we'll do this in next week's lab too. All right. Let's go back to this for a moment. If you place this piece of iron in a strong magnetic field, it becomes itself somewhat of a magnet, okay? Pole is here, and Will is here. Okay, has anyone else come in since the call roll? Okay. Now, this demagnetized piece of iron in a strong magnetic field then suddenly begins acting like a magnet itself. Take it out of the field, it probably is going to go back to being random and not magnetized. However, if you do something strong enough, then you could make this into a permanent magnet. For instance, while it's in that strong magnetic field, strike it, do something that the word I'm trying to think of is perturb. I'm not sure y'all understand what that word means. Perturbs, mix it up, and then suddenly the fields become more permanent. Okay? Now, have any of you ever experienced an electromagnet? We're going to talk about that in a few slides, but what happens there, you're running a charge around it, we'll get to this later, and the iron core becomes magnetized. You turn off the juice and it's demagnetized again. It goes back to being what it was before. And they use this characteristic down in shipyards and places like that where they're loading the big cargo ships. They'll take some big strong electromagnet and this truck comes up. The trailer of the truck is it's metal, iron, so they turn on the juice. It becomes a strong electromagnet, pick it up, take it to the ship, put it exactly where they want it, and then turn off the juice. It's no longer magnetized. So that is an example of this. Okay, putting it in a field, taking it out of the field. But if you perturb it, okay, and here's what I mean by that. And we'll actually do this in lab if I can find a pen that's not magnetized. And usually I can find at least one. But sometimes they run in short supply. Okay? If you take a magnet, you probably did this sometime in your youth, rub a piece of iron, cobalt, or nickel against the magnet. You're rubbing. You're not just bringing it into the field. You're rubbing it. The friction perturbs, shakes up those things, gets them to align more permanently. You take it out, you just made a magnet. Okay? And we'll do that in lab if I can find a fairly unmagnetized pen. I've been doing this so many years, all my pens are magnetized now, but if some of them have lost some magnetism, we'll do that. Okay? If I can remember to bring a non-magnetic pen from home, I'll do that too. Okay? So you can actually make a permanent magnet because you actually did it. Now that's not the only way. Here's one other way. And this actually happened to me. I think early in the term I was telling about digging out the patio, right? Okay. Before that summer, before that job, the old, we had a garage here, and then there was an old storage shed that was literally falling apart, leaking like a sieve. Who knows what kind of animals were living under the floor. It was a hazard. And then there was the privacy fence that picked up from garage, storage shed, and picked up there and went to the corner, separating our yard from the neighbor's yard. Well, I had to take the shed down. It was going to fall down one of these days, and I could have been in it, or something sort of valuable could have been in it, and, or lawnmower or something like that could have gotten rain. Just had to go. Well, when that went there, part of our privacy fence went. And also, when we had bought the house, we noticed the stakes were about 4 feet over from where the privacy fence was. And I asked our neighbors, they were renting, they asked the landlord, she lived in Tuscaloosa, and she said, yeah, the property line is 4 feet over. They just put the privacy fence in line with the garage, the shed, and the corner. They just did it there, so we've been mowing 4 feet of your yard, okay? Using 4 feet of your yard. So we didn't care, they didn't care. I said, well, I've got to replace the fence anyway, and is it okay to move it back to the property line? Oh, sure, do it. So I had to dig some post holes, and I was going to put up a little bit better privacy fence than what they had, but it was going all the way down to the garage too. Okay, so in doing that, and it just happens to be our yard, the backyard faces due north, the front yard. I mean, that boundary line was almost due north and south, south to the front, north to the back. Okay. Well, I knew that the panels that I was going to use for the privacy fence were 8 feet. Okay. So I planted posts, put a corner post in, and put posts every 8 feet. So I could do it and measured it all out. Unfortunately, it was a pretty steep, not steep, but a fair hill going down there, so it was going to drop. So each panel was going to sit down a little from the other, but I had to have everything lined up pretty well. So I put in the corner post up here and the one down at the garage. Okay, put them right on the property line best I could. Got those planted really well, and then I was going to run a string from the top of this one to the one up there, and then plant my other post along that string, so they would be right where they needed to be. So I was down there, facing almost due north, with a hammer, going to put the nail. And because the hill was up there and I was down here, I needed the nail as high up in the post here as going to be lower on the post up there. So it'll make it fairly level too. So I was up here hammering the nail. And I'm not a very good hammerer. My father says it's because they were right-handed hammers and I wasn't. So, but he didn't quite convince me of that, but that's what he always told me. So anyway, I was hammering away, and it was a tough old post too. And after a few strikes, I thought it was going in, and because it was, sort of loose, I was holding, and there went the nail. I couldn't see where it was. It was a lot of grass and stuff down there. And I dropped it. I just happened to be hanging the hammer down, okay? And I bent over. I didn't mean to have the hammer there. I just did. It was in my hand. I was looking for the nail in the grass, and suddenly the nail attached itself to the hammer. What? Okay. Well, what had I been doing? Remember I said, facing due north. Hammering due north. The Earth's magnetic field lines. The Earth is a magnet. Magnetic field lines were pointing north to south. So I was hammering, perturbing, the metal, the iron that was in the nail, in the along the direction that nail became magnetized. And my hammer did a little bit, but it was mostly the nail, and it was then attracted to the iron in the hammer head. I had just made because I perturbed it in the presence, not that strong of a magnetic field. The Earth's magnetic field is not that strong, but I was lined up just about perfectly that way and made myself a magnet. Thank goodness, because I'd have had to get a new nail, and I'm too cheap for that. Okay, so never mind. Okay, so that's what happens when you perturb, vibrate, a magnetic material in the presence of a magnetic field. That's how you make another permanent magnet. So let's move to the Earth's magnetic field. I already had a good segue into this. Where does this come from? I'm going to give you a clue here. I think I've already said it before. And I sort of hinted at it just in the last slide or two. What is a magnet? What makes a magnetic field in the first place? We say a pole of a magnet. What makes that? A moving charge is what induces a magnetic field. A moving charge always induces a magnetic field. Okay? So, remember, back here, we said it's the spin or the orbiting of those electrons. Electrons are negative charges. Moving, either spinning or orbiting, they create a magnetic field. Every moving charge creates a magnetic field. Every atom has electrons going around it, but their fields tend to cancel out. Only iron, nickel, and cobalt, can they realign? Will they be permanent magnetic moments? Okay? So, guess what I said the interior of the Earth was? Mostly iron. And probably number 2 is nickel. Okay? 2 of the 3 naturally occurring magnetic materials. Well, and I also mentioned before the structure of the Earth. We live on the crust. The crust is almost paper thin. I mean, it only goes down to a few miles. Compared to the Earth diameter, that's paper thin, okay? So it's really, really thin. Underneath that, they call the mantle, okay? In the mantle, most of the elemental constitution is iron. It's not as much total iron as the core. But inside the mantle is a molten, meaning melted, core. Just think, that's what a volcano just happens to have found a crack in the mantle and in the crust, and that molten material makes its way to the surface. That's where it comes from. The core, outer core of the Earth, is molten, melted, mostly iron, some nickel, magnetic material. Okay? Now, the inner core is solid again. Okay? Just because of all the pressure and stuff, it can't remain a liquid. Okay? But that's beyond, that doesn't make any difference to what I'm about to say now. So here we have a spinning Earth. The Earth is spinning pretty fast. Okay? The inner part of that is liquid. Okay? The outside of that is, again, mostly iron material in the mantle, going around. The liquid doesn't spin as fast as the iron, right? As the solid. Solid has to spin. It can't not spin. The liquid gets bumped against, and it's not a smooth interface. There's jagged things and stuff like this, so there's all sorts of friction in there, and friction knocks off electrons. So now we have moving charges creating a magnetic field. It originates deep beneath the surface from currents in the molten core. That's what makes the Earth a magnet. Because its core is mostly iron and nickel, moving charges, magnetic. So, and this is where we get back to the thing of north or north-seeking pole. What did I say about poles? Which ones attract, which ones repel?
Like charges repel.
Okay, charges, but poles too. Like poles repel. So, unlike poles attract. So, if I have a compass needle pointing to the north, okay, this point is attracting that pole of the Earth, right? So what do we call this point? A north. And what does north attract? South. So either that's the south pole of the Earth, north, or this is a south pole of the magnet, okay? So that's why we really should call that a south-seeking pole. But no one calls it a south-seeking pole. They call it a north pole. I mean, a north-seeking pole. They call it a north pole. Well, calling it a north pole would then make that. So that's why in the magnetic north pole of the Earth is really like a south pole in the Earth's magnetic field, because the field lines, the north field lines, well, all magnets, they're going toward that. So that would make it a south pole, which is dumb, but it is true. Now, there is a problem, Houston. Uh-oh. One would think that because the Earth spins around its axis, that therefore the North Pole, with all the charges moving sort of like this, that the magnetic North Pole would align itself with the actual axis of the Earth. Not quite. Unfortunately, the magnetic North Pole of the Earth, this globe shows it right there. It's inside the Arctic Circle, which is 23.5 degrees from the North Pole, but it's well inside. So it's about 18, 20 degrees off the North Pole. So it's not aligned itself with the actual pole of the Earth. It's close, but no cigars. Okay? Now the south one's even worse. Okay? The south magnetic pole is just outside the Antarctic Circle, which is 23.5 degrees. It's not much. It's about 24 degrees from the South Pole, but that's pretty far. The other one's like 18. This is 24. So they're not really quite lined up. And because of that, since a magnet, a compass needle, is going to point itself toward that magnetic North Pole, then unless you're lined up with the North Pole, North Magnetic Pole, the compass needle is going to point wherever that North Magnetic Pole is, not necessarily where the true north is. So you do have what they call magnetic declination. That's that little bit of offset of a magnetic compass from a gyroscopic compass set. And when I was in the Navy, we always had to account for that, because we had gyroscopic compasses that we did all our navigation by, but they all depended on power supplies and everything else. And if we ever lost power, we could lose those. So we always had a backup of a magnetic compass. And then we had to calculate the offset from wherever we were on the planet. And we'll see that next. The direction of the field, okay, let's stop there and show this slide. This is the one that's the figure in the book. Okay, sorry, I should have done this one earlier. This is one that's also on page 157. If indeed the Earth acts like a magnet, so imagine a magnet in there, since the field lines are pointing toward that, all your little north poles are pointing toward that, that makes that a south pole. So we really should have all along called those others north-seeking poles and south-seeking poles, and then turned the field lines away. But you see, it's all out there in the literature and everywhere else. So this is the reality. Okay? Sorry about that. Someone sort of screwed up. We weren't thinking through. Here is a picture of the U.S., and as you might notice, the North Magnetic Pole, like I said, was in northern Canada, way up there, in the Bering Islands there, way up there. And you see where we live in Alabama, it's not far from being in line with the true north. It's a little bit off. A little bit, not much. So therefore, these are the lines of what they call declination or offset. And it's hard to read, I'm sure, from where you're sitting, but if you got your book, you can see it for yourself. Here is the zero declination line. Goodness gracious, that goes through just a little bit of Florida, not too far from Tallahassee maybe, okay, up through southern Georgia, a little bit east of Atlanta perhaps, maybe Athens, Georgia, and then going on up, almost hitting Chattanooga on the nose, going up through central Kentucky. I would guess Richmond is somewhere pretty close in there. I'm sorry, not Richmond. Kentucky, I can't think of the name. But anyway, then almost up the Ohio, Indiana line, and then going up through part of Michigan here. That's the zero. We're over here. Birmingham is almost right there at, I can't read that, 2 degrees east, 2 degrees offset. So we're almost on the money, okay? This is 4 degrees. I can't read those. Look at the book. No, 6 degrees, 10 degrees, that weirdly spaced here. And up here in Maine, you're 18 degrees off. So just using the magnetic compass, you're not going to be hitting too close, because you see up there, north magnetic here, and the true north is there. Down here, they're closer to each other, not quite. So going this way, that's by twos, isn't it? 2, 4, 6, 8, 10, all the way across. But by the time you get to Washington State, you're off again by, what, 22 degrees? Yeah, so you're not too good there either. Now the north magnetic pole is over here, true north is here, so you're off a pretty good amount. So we happen to be in a location, we're not off too far doing that. Now, when I was in between jobs, when I worked at Southern Research Institute as a research physicist there, we did mostly radon research, but I did some other air quality stuff too. And then before I started teaching here at what's then Western State Tech, there was a year there I was in between, and I just did anything I could. I was adjunct at Jeff State, and I was able to get a job as a sampler, soil sample, for, it was in some lawsuit. I never knew which side I was on, but it was in some lawsuit over in Anniston, Alabama, where what used to be Monsanto had dumped PCBs into the creeks and stuff there, and people who lived along the creeks, a generation or two later, were getting cancer like crazy. And so it was a big lawsuit there. I was over there taking soil samples, and I had to do an array of samples certain distance from where the site was, and take samples all along, up and down mountains. It was a wooded area, and all I had was a magnetic compass. But fortunately, Anniston, being in between Atlanta and Birmingham, I didn't have to adjust too much, because I couldn't get more than a degree or two anyway, so I wouldn't have known which way to adjust. So I could just follow the compass line and take my samples that way. And it worked out okay, I guess. I never knew what it was used for, who won, who lost. I had no idea. They just paid me to do the research. Okay? So that's what we mean by the offset. Now, here is a feature that I am completely baffled by. I don't see how in the world it's physically possible. My understanding of why it happens anyway. And it's a mystery. To me, a total mystery. I have a little bit of a theory, but whether it's anywhere close to reality, I don't know. there is ample evidence, more than one place, lots of evidence that the direction of the Earth's magnetic field has reversed itself periodically since the Earth has been around. Okay? And what it's based on is, you know, the theory of plate tectonics. There are plates that separate and there are plates that are grinding together. Pacific is where they're grinding together, the Ring of Fire, all those volcanoes and earthquakes and stuff they have mostly along the Pacific. The mountain ranges there are high because, you know, it's been building up. Okay? In the Atlantic, in the middle of the Atlantic, that's where the separation happens. So you can go down and do cores in the ocean bed, but also in the continents, you know, Europe, North America, Africa, South America, and do cores down there, and you'll run across places where, okay, now get this, where there's been volcanic activity. You have multimaterial coming up, and if that multimaterial cools when it's lined up with the Earth's magnetic field, then there's a good chance that's going to become magnetite. If it cools counter to that, or some other way, then you'll just have hematite. It's iron ore. They're the same iron ore. It's just some is magnetic and some is not. So that's the feeling of what's happening. So if they do these cores down here, they will periodically find a core of magnetite. And they keep going down, and all of a sudden, they'll run into sometimes when there's hardly any magnetic material, and then later they'll find another where it's getting stronger again, but the polarity is reversed. What? Okay. First thing that pops to my mind, Earth hasn't changed direction of its spin, so how in the world could that happen? Okay. And I don't think anyone believes that's the reason. The second thing was, well, these are separated by periods that there wasn't much magnetic material. Oh, maybe that's what's going on here. And the magnetic fields of the Earth seems to strengthen and weaken. Okay? There could be something here. I don't know if this is what they think it is, but it's the only thing that makes sense to me. Have you ever seen a sine wave? Sometimes positive, sometimes negative. Sometimes positive, sometimes negative. Well, what if the actual spinning charge centers in the middle of the Earth, what if it actually is precessing for some reason? And I can't imagine why. And when it's like this, then you have strong magnetic field lines like this. But then when it moves over here, the field lines weaken and weaken, and soon you have none. And then they strengthen again, but are pointing in the opposite direction. And what if over a huge period of time, this kind of motion is going on? That would account for periodic reversals. I can't think of anything else that can. Now, I may be completely off base with that. When I talk about this doesn't happen much, the last reversal was 780,000 years ago. Guess what? That's not during my lifetime, okay? It's not during the time that mankind has been in existence, you know. Who knows what had happened. But you see, the Earth's been around, they think, for something on the neighborhood of 10 to 12 billion years. So it's had time for many reversals. I think they say in the book something like 22 reversals. It may not be in this chapter. It may be back in the back part of the book. I can't remember which one, because we studied this in physical science, the 111 as well. Let's see if it says it here. I think it's in the other part, that they think they've discovered at least 22 times it's reversed itself, because we studied the plate tectonics in 111. So, don't know. We just happen to have lived our entire lives at a time when we've been in fairly strong, one-directional magnetic field of the Earth. It may be that sometimes there were no magnetic fields. Other times they were pointing the other direction. Okay? So, why would all this happen? Whenever you have a moving charge, and what do we call a moving charge? An electric current. A moving charge is an electric current. Whenever you have an electric current, you have a magnetic field induced. Every time. Moving charges, which are currents, produce magnetic fields, period. Every one does. Okay? Here is one illustration of this. Okay? Here we have a wire going through, say, a piece of cardboard, piece of paper, usually something a little more sturdy than paper, like cardboard. Punch a hole in it, send the wire through. Put a pretty strong current through that wire. Now, what kind of current? Say again? I can't hear. Okay? There's two kinds of currents. Okay? Oh, I know what you're thinking. That's one kind. Direct current or alternating current. Which kind did you better put across here? Direct. Why? Alternating current? The charges are moving like this. Guess what your magnetic field is going? You don't have it. Okay. That's why you don't notice with wires that you ever have a magnetic field induced, even though you have pretty low voltage, maybe pretty high current, because alternating current, they're constantly changing, so they cancel each other out. With a direct current, DC current going through here, the charge is moving in one direction. Now they're showing the electron charge here, okay, as you were talking about, as opposed to the conventional charge, which would be moving the other direction. If you had that strong thing, now one thing you could do is sprinkle iron filings on the cardboard here, and you would see them line up like this, okay? What they are showing here is put a magnetic compass there. And it may not, here may be true north there, but you put it in the presence of this, and you see it turning here, move it here, and it turns around like this, okay? So obviously there's a stronger magnetic field there than the Earth's magnetic field, because that's influencing the compass. Now, I hate that they did the electron current here. The convention is to use the conventional current. And if you point your thumb on your right hand in the direction of the current flow, conventional current, direction of positive charge removed, if it were moving, then your fingers on your right hand are going to point in the direction of the magnetic field. Okay? And that's what we're seeing here. It's just that they had electron current here, which would be here, so that follows the left-hand rule, which no one talks about a left-hand rule because they're biased against us. No, well, okay. All right. The shape of the field is determined by the geometry of the current. Now, what do we mean by that? A straight wire produces a circular field. Okay? That makes sense. But what if you had a current loop? Not a straight wire, but you make the wire into a loop. Well, use right-hand rule. Guess what? Your fingers are pointing toward the inside, coming from the outside, so north is pointing that way, south would be the other way. So that would be a current loop is then going to create something, and you have enough of those, and you create a solenoid. Y'all have solenoids in cars, right? Okay, they're basically used in switches and things like that, right? Is that right? Correct me if I'm wrong, but that's my perception. Okay? So, here it shows, again, this is showing the electron current, and so I'm going to do the positive current, and you see this time they have it moving this way, and so therefore the arrows are pointing up toward the center, down on the outside, so that would be, I think, the north, north upward, okay? Make sense? Do a whole bunch of those, and you strengthen that, okay, as long as you don't kink it and turn it back the other way. And the more turns you have, the stronger and stronger magnetic field you have. And that basically is what makes a solenoid. Okay? So this is the global view of that we just showed. Again, I'm going to do it in the sense of the, they had the current. The electron current this way, the conventional current that way. So, yeah, it's going like this. So the north is up, south is down. So that induces a magnetic field. A pretty weak one if it's just one coil and not too much current. But if you have lots of coils with a decent current, you can induce a pretty strong magnetic field, often called the solenoid. Okay? And here is I think a relatively good example of the solenoid. Again, we have a battery. Why a battery? To produce what kind of current?
DC.
DC current. Okay? So all your current, and again, I like to do the conventional current going this way, and you see the current be flowing like this, so your fingers are always pointing in that way. So there's your north pole, here's your south pole. That can be a really strong magnet. Okay? Induced strictly by the flow of the current. A moving charge always induces a magnetic field. And put enough current loops in there, and you can produce a pretty strong magnetic field, depending on how much current you have too. Okay? So that leads to electromagnets. Okay? So where we are now, we just entered 6.4, electric currents and magnetism, current loops, and now we're doing applications of electromagnets. We're over on page 160 now. Now, I don't know if this is absolutely necessary, but it's what I usually think of. If you just have a coil there, that basically is equivalent to a solenoid. If you put a ferromagnetic core in that coil, the words sound alike, but they're different, core in the coil, and what is ferromagnetic? What does that mean? What three materials? Iron, cobalt, and nickel. Exactly. Put a core in there, and now you've got an electromagnet. Now, the current carrying wire is wrapped around that core, that ferromagnetic core, and now what was a field just from the coil is now emphasized in the core, ferromagnetic core. The field is enhanced by that combination, and what's more, it can be turned on and off. Turn on the current, you've got a magnet. Turn off the current, no longer a magnet. Those domains go back to the random orientation. Okay? And that's what I was talking about in the shipyards, picking up. And it used to be what they did, they had crates, usually wooden crates, and they had to put cables around them and tie the cables and make sure they were good, lift them slowly, make sure they didn't wobble, and it was really, it had a lot of accidents too. If something jarred and stuff, things would fall out and huge crates would fall down on people. It wasn't very safe. Once they went to electromagnet, turn on the juice, move it over, set it down, turn off the juice. It was so much easier and safer process. Okay? Now that's one application. Every meter you have has an electromagnet in it. Okay? We'll be using in the lab today, we'll be using an ammeter. The voltmeter will be in the voltage supply, so we're actually using one there too, but you don't see it. But what the ammeter is, and we'll have an illustration of this later, it basically has electromagnet. The more current that's flowing through it, the stronger the electromagnet, the more it deviates. Less current, it goes back. Okay? That's what moves the needle on the meters. Now, I know most of you only use digital stuff now. You use anything with a meter on it, with a pointer on it? Probably you do. Well, good. I'm glad to hear it. Okay. And many meters do. We'll use digital. Sorry. We used to use meters with switches. Okay? Again, when you exceed a certain thing, it switches on. When you fall down, it's off. It's probably electronic now, but the box that used to be there on our thermostat, that's what they're going to mention. No, they don't. I thought they were. but a switch, a heat pump switch. Okay? Say again? Yes, exactly. It has that mercury bulb in it, and when it tilts one way, it turns, say, the heat on. When it tilts the other way, it turns the air conditioning on, right? Okay? Now, what is making that happen? The stronger current that goes through here, okay, the weaker current, that's exactly what's happening. Most switches have electromagnets in them. Speakers, okay, say again? Yes, they have electromagnets in them. Motors, generators, everything pretty much has electromagnets there. Let's look at the meters at first. Now this could be for measuring current, okay? Now here's the thing. Now that's a weird looking needle on it. Looks like a pencil to me, but you know, whatever it is, that's a needle. Okay, it's fixed to the axle here, and when you have more current flowing through it, then, okay, time out. First you have a big, strong, permanent magnet here, okay? North pole here, south pole here. They call this a horseshoe magnet, okay, because of its shape. So the field lines are almost uniformly going from left to right, away from the North Pole toward the South Pole. Because of the shape and stuff, they're almost uniform, parallel field lines. Okay? Now, place in there a coil, and you have a coil, and whether this is electromagnetic material or not doesn't really matter. This could be more like a solenoid, and as the juice turns on, this becomes a stronger magnet. Well, depending on the rotation here, if more juice goes on, it becomes a strong north pole. Well, where is it going to turn then? Away from north and toward the south. Less current, it goes back this way. Now, there's usually a spring on it that's keeping it down here. That's where you zero it. Okay? When there's no current, it's at zero. When you have current, it swings it this way. No current, it goes back to zero here. Okay? There is a ammeter. Okay? Change the properties of change the scale of it basically, and you make it a voltmeter. Invert the scale on it, and you make it an ohm meter. Okay? Because the resistance is inversely proportional to the current. Okay? So it uses a magnetic field produced by the current, and the magnetic field enhances the deflection. It's proportional to the current, but you can modify it to be a voltmeter because, see, the more voltage you have, the more current you have, right? Ohm's law, directly proportional. So all you do is change the scale of the meter from amps to amps to volts. Resistance, you have to reverse it. In fact, a lot of if you have a single scale and you have it set for an ohm meter, basically, whereas an ammeter and voltmeter read 0 to whatever, max, your ohm meter will read from 0 to max this way. It goes in the opposite direction because it's inversely related. So they can be modified slightly electronically, but mostly by scale to read your potential, which is potential difference, voltmeter, or resistance, an ohm meter. Okay, electric switches, electromagnetic switches. Now, sometimes these are called relays, and other times solenoid switches. There's slightly different applications or uses of them. What a relay uses is a low voltage controlling a high current. So that's why they call it a relay. A little thing controls a big thing. And this is your glass vial, mercury glass vial that you were talking about. Here's your small battery in here. Very small current relay circuit. Okay? It just is enough to make a little field. Okay? Now, here's your bimetallic coil. This is a thermostat. Okay? As it gets warmer, it tends to expand this way. It gets cooler, it contracts this way. So if it gets warmer, it'll open the switch and pull that away. Going this way, it actually closes the switch and it pulls back in. But what it's doing is adjusting the current in this electromagnet. Okay? And when it gets strong enough, it closes the switch and then it starts the heat pump. Okay? If it gets warm enough here, it opens the switch and the heat pump turns off. Okay? That is a very simplistic model of how a relay, a very small current relay circuit, can control a huge thing like a heat pump. And it's pretty energy efficient to do it that way. You don't want the whole circuit being controlled by that. You'd have to be running the same power through it all the time. Okay, now solenoid switches are pretty similar. Movable spring action loaded iron core. Okay, this time the iron core is spring loaded, responds to the solenoid field. The water valves, automobile starters, VCR switches, all these things, activation of the bells and buzzers, these are all that. If you think about it, when you're changing the channel on your remote, all you're doing is pushing a button. What that does is closes a very small, and you remember all your remotes have batteries in them, right? When the remote doesn't work, you change batteries, they work again. You have a very small current circuit there, and when you press the button that closes the circuit, and then it starts the electronics to change the channel or turn on something, turn off something, you know, whatever. Ring bells, activate buzzers, whatever. Remote car engines. Some of the Ford products do have those, right?
The electric stuff?
Yeah. Yeah. You can press a button and your car starts, right? You don't have to turn a switch anymore. Am I right? All mine are old ones. Okay. I still turn switches. Okay. Okay. So, all these are, anytime you have anything like that, electromagnets are involved. Big time. Okay. Now, whether you think about it or not, telephones, loudspeakers, stereo speakers, all these things have electromagnets in them. What they do is couple acoustic waves to electric currents. That's exactly how they work. And even the receiving end has electromagnets in them. So electric current can then produce a sound wave, and you can hear. So let's look at the telephone. I think this figure is going to be here. Here's Alexander Graham, here's some old dude, okay? And he's speaking into the receiver here. Now, phones used to look like this, folks. I don't know if any of you remember them, okay? Never mind, okay. It was kind of a joke, okay? And what's happening there? He's speaking into the speaker, and if you hold your hand near your mouth, you'll feel little vibrations, right? That's what sound travels. It's compressing and rarefacting air. Little vibrations. That's what's happening. So those little vibrations, these are good. Condensations here, the rarefactions in between. Condensation, rarefaction. Well, these go into the speaker, and they have little holes in the speaker, okay? They go in, and they hit a metal diaphragm. And that's a very sensitive little metal diaphragm, and it moves back and forth, depending on if it's condensation or rarefaction. Back and forth. Well, this little diaphragm is connected or compresses carbon granules. Sometimes they're compressed, sometimes they're not as compressed. Well, what that does is change a current, okay? And that changing current then is what sends the message through the wire, okay? Now, on the receiving end, the speaking end, you have a permanent magnet here, and then you have an electromagnet. I don't know why they have the space here. And this electromagnet, and depending on that receiving signal you get here, whether it's high current or low current, and they're all very, very small, if it's high current, then it pulls the permanent magnet toward this paper cone and compresses air, rarefacts and pulls it away, and the same signal that went in here comes out here based on the current change there from the granules creating a current change here in the electromagnet, pulling and pushing against the permanent magnet, and that vibrates the paper cone and sends out the sound waves again. So the sound waves create an electric current. The electric current creates a sound wave. Now the amazing thing to me is, most of the time, when I pick up the phone and someone speaks, if it's someone I know, I'll almost recognize the voice. So not only does it transmit a sound, but it transmits it in the frequency, pitch, and everything else that you'll recognize almost every time who's talking, if you know the person. Of course, most of the time you don't know who's talking. Or if it's one of those computer things, never mind. Okay. So the speaker, the varying current changes a field of the electromagnet, moving the permanent magnet backwards and forth, which moves the moving magnet, vibrates the spring attached to the paper cone, which then produces sound. Impressions are effective, depending on the motion there. And you'll make almost the same sound. Okay. A speaker in a stereo system, same thing, only much bigger, okay, much louder. Okay, let's move to electric motors. Now what an electric motor does is convert electrical energy into mechanical energy. Now how in the world does this do? It has basically two working parts, and that's all. The first is the field magnet. Here it is, just like we saw before in our meters. Big, strong north here, they reverse the side, south over here. So all your field lines are going almost straight, parallel field lines going from north to south. Create permanent field. Okay? That's the field magnet is stationary. Magnetic field lines, permanent, stationary, uniform, very nice. Then you have an armature. Now that's a movable electromagnet. Okay? So here's an electromagnet. It's going to, they don't show the power supply here. It's somewhere down here off site, okay? But it's sending electrons here. They don't define what this is, but it's an electromagnet here too. But over here, it's coming in, and these are brushes, okay? They're here and here. And halfway around, the brushes are touching, say, a positive charge, but then when they get more than halfway around, they reverse and touch the same brush and touch a negative that was touching negative will touch positive. That's the key here. Because when you first turn on the juice, you provide the electrical energy here, then this coil here, this was just neutral before, nothing yet, just hanging in there. And if when you turn on the juice, this becomes a strong north magnetic pole, electromagnetic pole. This is south, that's going to turn it this way, right? It repels from the north, hits the south. So it turns it there, and just about the time it lines up where it wants to stop, the brushes reverse. And when the brushes reverse and hit the other end, then this end becomes south, and that end becomes north, and now they're repelled again. And they just keep turning and keep turning and keep turning. That's exactly how an electric motor works. Your weed eater, if you have an electric weed eater, motor on a ceiling fan, anything, this is exactly what they're doing. Okay? The armature is a moving electromagnet, rotates interaction with the magnet, field magnet. Okay, now you've got two things going on here. One or two. We have what we call a commutator. Now, they used to have these in car engines. They probably don't anymore, do they? You probably don't run into commutators anymore. We'll talk about them and we'll see them in lab. But you do have them? No, okay. Y'all have dual diodes or tri-diodes or something like that, right? Yeah. And those do the same thing. A little bit better, perhaps. Okay, they don't wear out as much. But we'll talk about what the commutator is. And brushes, and that reverses the current to maintain rotation, just like I was talking about here. You can't see that part of it, but that's the part that reverses the polarity. Right about the time the north gets to line up with the south and the south lines up with the north, then it reverses, and then this becomes a south, that becomes the north, and then it keeps it turning. That's what the commutator and the brushes reverse the current to maintain the rotation. Okay? And that's how an electric motor works. Now, I know you have electric motors in cars, right? What do we call that? The starter motor, because that's an electric motor, a DC motor that starts the process and then the internal combustion takes over, right? Okay. Now, we're going to go to section 6.5, which is electromagnetic induction. Let me make sure I haven't skipped any examples. I don't think they've had any because it's hard to do problems with these. No, the last example was, we did right at the end of the last class. Now, remember what we said? What creates a magnetic field? What creates a magnetic field?
North and south.
What?
North and south poles. North and south.
Okay, those are in magnetic fields, but what creates that?
The iron.
Okay, what's in the iron that creates that? What creates a magnetic field? Always. Okay, a moving charge, an electric current. Every time you have a moving charge, you're creating a magnetic field. Okay, now we're going to reverse that. Electromagnetic induction, the causes are anytime you have a changing magnetic field, guess what you do? Induce a current. You create an electric current. So you see a moving charge, which is electric current, creates a magnetic field. A changing magnetic field induces an electric current every time. Okay? So, the causes are any kind of relative motion between your magnetic field and your conductors. Okay? And what they mean by that, you could be changing your magnetic field, keeping the conductors constant, or you could be changing the conductors, keeping the magnetic field constant. It doesn't matter. All you need is relative motion between the two. Okay? Here's sort of an example of this. Okay? If you had a coil of wire here, and it was just a coil of wire, notice there's no battery associated with this at all. None. No battery. And you just had a coil of wire, it's going to be sitting there at 0. This is measuring current, by the way. Okay? Probably in milliamps or something like that. 1 milliamp, something like that. So you have this coil of wire just sitting there. You have a magnet way up here. Okay? And you decide to drop the magnet. Okay? When this north pole falls through that coil of wire, now you have a changing magnetic field as the north pole. Think of those field lines. All those field lines are concentrated at that north pole. So there were none cutting that coil. Suddenly a bunch of them cuts it, and then none are cutting it again. Changing magnetic field induces a current. Sure enough, there goes a positive current. Okay? Now, if you wait just a second, fraction of a second or two, until the south falls through, what's going to happen then? Negative current. Because that's the opposite field line. But you're changing the magnetic field lines. Even though it's moving in the middle, you have no current there because there's not many field lines there. Now, if you did it the other way and moved the south up this way, I think they have this backwards, but if you flipped it over and did the south down this way, then that would make a negative, and then when the north came through, it would be positive. When you're moving them this way, I think the south moving this way is the same as the north moving that way, but we won't argue with them here. But again, changing magnetic field lines being cut reduces the current. So you created a current, not by a battery, but by changing the magnetic field. Okay? How do you change the magnetic field? You either turn the magnet and keep the coil steady, like we have here, or if this magnet was somehow fixed and you did the coil up and down, same property. So you can move the coil with a constant magnetic field, or move the magnet in a constant coil. Either one will produce the same thing. Changing magnetic field line near conductors. The effect is an induced current and an induced voltage. Okay? The induced voltage depends on how many loops you have. Why? Because the more field lines being cut, the stronger the field, the stronger the current. The fewer field lines being cut, same number of field lines, but it's cutting fewer coils, then the weaker the current. That's one. The strength of the magnetic field. If this was a very powerful permanent magnet going through, then you're going to create more current. Very weak magnet going through, a smaller current. And thirdly, the rate of the magnetic field change. If you very slowly lower that through, remember current is charge per unit time rate of change of charge. You're moving charge, but at a slower rate, so it'd be a less current. And then less current this way as that moves on through. Or if it goes through fast, it might be greater, but it won't have as long a duration. All right, make sense? So those are the three properties for electromagnetic induction. Now that leads, okay, I'll go on and do this and we'll get that, to what we call a generator. Now I can't remember which they had first. Seems like they had electric motors before they had electric generators, but that doesn't seem like it would be the case. One way or another, it was early in the field of useful electricity like this, and there was a World's Fair somewhere. It seems like it was St. Louis. And this technician went in to set up the demonstration of whatever it was that he was trying to demonstrate, either a generator or a motor. I just don't remember which, but he wired it backwards and he created the other one, okay? Because one is the inverse of the other. The structure of a generator is an axle, remember that, with main wire loops in a magnetic field, just like we had for an electric motor, but this time you turn the axle mechanically and you produce electrical energy. Before, you turned on the juice and it turned the electric motor. You use electrical energy to produce kinetic energy, rotational motion. With a generator, you turn the axle and create electrical energy. That's exactly what a hydroelectric dam is doing. The water turns a turbine, the turning turbine produces electrical energy. It's just the reverse process of what a motor did. If it's a steam generating plant, you've heated the steam either by burning coal, burning natural gas, burning gasoline, nuclear power, whatever you use to create the steam, it turns the generator and then you produce electrical energy. So, most of those are generally producing alternating currents. In fact, I would say they all really are producing alternating currents, but you can have a DC generator too. We'll get to that in a second. Let's look at the alternating first. Okay. This is the setup just like before. Here's a strong permanent magnet, horseshoe magnet. Field lines are going, they show them this time, going parallel, constant. That's a permanent electric field there. Okay? Now, sorry, this is not quite the same. This is electromagnet. I just noticed they have the field coils here. This is not a permanent magnet, it's electromagnet, but it's a strong one, okay? Now what we have here is two terminals with brushes. This terminal is attached to one end of the wire and this terminal to the other end, okay? Now, what you have is something turning the axle here, okay? Turning that coil within the field here, okay? The mechanical energy is doing this, okay? The magnetic field lines are constant this way, okay? As you turn this coil in that constant magnetic field, right now the maximum number of field lines are cutting through that coil, right? So you got the maximum potential current being created. You turn this somewhat, and you know your water, your steam, something is turning this. You may be hand cranking it, okay? You're turning this, and as you turn it, you're decreasing the number of field lines. And any time you change the number of field lines, no matter why you're changing, which way you're changing, you're inducing a current. Changing the number of field lines being cut. So the current is decreasing till it basically goes to zero here, then it starts increasing, but going in the opposite direction, right? Because now it's increasing, and then it maximizes here, decreases again, and then it goes in the opposite direction here. So what you get out of this? Alternating current. Positive, negative, positive, negative. Zero when it's like this, maximum when it's like that, and alternates every time it turns. Alternating current. Induced voltage and induced current changes the signs. A good old sine wave, S-I-N, sine wave, changing the S-I-G-N signs from positive and negative. Now, how would this ever produce a direct current? It doesn't produce a nice, steady, even direct current, but it does send current in one direction only, and here's how you do that. Here you have the same setup, everything's the same, except rather than having two poles here, your brushes are on, and this is not a solid ring, but a split ring. Okay? You have half of a ring here and half of a ring there. Now, at any moment, one of these brushes is touching one ring and one is touching the other. Okay? So when this is like this, maximum field lines are being sent through, so you're at some positive current is being induced in here. And as you turn this and change the number of field lines, now the current goes to zero. Okay? But you've also turned the brushes just about to the crack, and as soon as you go in here, and it was going to make a negative here, you flip sides, and now it makes another positive. And then right about the time it would have reversed, you flip sides, and it makes another. This is called a split ring commutator. And that's what they used to use in they called it an alternator, because you see your car is always generating electricity. And what kind of electricity is it generating? AC, except you need it DC. You couldn't charge a battery with AC. It'd be charging half the time and discharging half the time. Never would work. So they put in it, back in the old days, a split ring commutator, so when it goes halfway around and starts to change sign, then it reverses polarity and still. So it would be what I call a pulsed DC. Always the current is going in the positive direction the way it shows here. It's just sometimes it's zero, and sometimes it's max, sometimes it's zero. So that's a pulse, but it's always positive. So your pulse always charging the battery. So what your alternators are now are what? Tridiodes or dual diodes or something like that, that do the same thing, because the diode only sends current in one direction. Then when it would be doing this diode is working, this one's not, and then right about the time here, this one will work and that one will not. So you get the same process there. I'm probably really screwing up or oversimplifying it, but that's basically what's going on. Or am I right? Or do you know enough about it to know? I think that's what you have nowadays. Ask John Harris or whoever if you ask and see. Okay. But I'm pretty sure that's what they use. Except it seems like I've heard they use a tridiode maybe to even that out. I don't know. Maybe a dual diode, something like Okay, so the DC generator produces a direct current, but it's a pulse direct current. The sign of the current and the voltage is always positive, but it's not an even positive. Now you can use electronics to even that out, smooth it out some. Okay, if you need to. But if you're just recharging the battery, who cares whether it's pulsing or not? You're just recharging the battery. Okay. Now, there's a concept supplied at the bottom of the right-hand column on page 162, a simple generator, and they tell you how to do it. If you want to do that, you certainly can. There's a very interesting article, and I think somebody, maybe it was last night's class. See, I'm teaching a physics class at night that we're going over some of the same type material at a much faster pace than what we're doing in here. And I always am getting crossed up there what I've said to you as opposed to saying to them, and now I'm doing it in reverse. The title at the top is called A Closer Look. The title is called A Current War. Does anyone know what they're talking about there? Who are the two sides in the current war? Guess what two currents they were warring? Which two kinds of currents do we have? DC and AC. Okay. Yeah, or AC, DC. Okay, never mind. We won't go there. Okay. Now, what is your feeling on either one of those? Well, DC current is generally considered to be safer. Okay? It's only going in one direction. You don't have the alternating thing going on there. You usually have pretty low voltage. The highest I've heard of, I'm sure they got some higher than this, like those electromagnets probably use some super high ones. But car batteries are 12 volts. A diesel truck battery might be 24, right? And I think I've seen some bulldozers or things like that that may even have 36 volt batteries. Big old monsters there where you really need a lot of power. But still, it's pretty low. What's the voltage in AC generally? 120 and normal, if it's a clothes dryer or a stove, 240, and there are actually some things that are 360. Okay. Orders of magnitude higher voltage and considered more dangerous. They're alternating too. And what does your heart do? It's basically an alternating thing. It's beating or not beating. So AC can really mess with your system. DC may a little bit, but usually is because your frequency. What's a normal heart rate? Anyone know? Around 60 beats a minute, right? And what is frequency? Quite often, pretty close to 60. It's not beats per minute. It's 60 hertz or something like that. I mean, it's right down at the same thing, and that's why alternating current can really mess with your system. So, back in the day, when electricity was brand new, who was the earliest inventor that just did wondrous things with electricity? You all know him. I don't know if you can think of his name right now. Second?
Tesla.
I can't hear.
Tesla.
Tesla. Oh, someone said Tesla. Who was that? Oh, who? Oh, okay, Tesla. Okay, I was actually thinking the guy Tesla worked for originally. Who? You know this name far better than Tesla, I would think. Maybe you don't these days. Thomas Edison. Thomas Edison may still hold the record for the most number of patents of anybody in the world. I mean, he had, I think, thousands of patents. I mean, he created the phonograph. He created light bulb. I mean, just tons and tons and tons of things. Really a wizard. That's what they call it, the Wizard of whatever, Menlo Park or wherever it was he lived, okay? Incredible. But he was convinced that AC was dangerous, not to be messed with, and that you needed to set up things for DC. And this young guy that came into work in his lab, I think he was a Serbian or Croatian immigrant named Nikolai Tesla, came to work under him. And I think to begin with, they did quite well together because Tesla was a brilliant mind. Edison was a brilliant mind, but after a while, they sort of got on each other's nerves, I guess. But Tesla was convinced the way to go was AC. DC is real hard to transmit DC very far, okay? Because usually you have low voltage, high current, and you lose, energy line loss by current. Tesla was convinced AC was the way to go. In fact, he created and invented a lot of the stuff in electromagnetic induction, improved generation. I mean, he did all this. Tons of things himself, okay? And ultimately split ways. Tesla got a very powerful backer behind him named George Westinghouse. Name ring a bell? And Westinghouse backed the AC side, and actually they won. Even though Thomas Edison is generally far more well known, it was actually Tesla and Westinghouse who won the wars, you might say. So, anyway, pretty interesting. Might be, I can see at least 4 or 5 paper topics just in that little boil alone. If you haven't chosen one yet, guess what, folks? You got 2 weekends left to write your papers, okay? Meaning this weekend and next week. I will accept papers on Tuesday of next week, of the following week, but Thursday you're losing points. Okay, so get the papers in, preferably next week, okay? But if not next week, Tuesday's drop dead day, okay? Before you start losing points. All right, now let's move to, we've done generators, now let's do transformers. What is a transformer anyway? Any idea? What does a transformer do? Maybe transform something? Okay, what would you transform? Now, I already have hinted at it in what I just said about DC. Where do you lose energy? Because of line loss. Say again?
Distance.
Say again. Over long distances, and what loses it for you?
Current.
The what? Current? Absolutely. So you don't want high currents, you want high voltage and low currents. And you see those are connected because you see your power in equals power out, right? Those have to equal. Conservation of energy. Power is energy per unit time, so in the same time unit, energy in equal energy out. Let's talk in terms of power now. So the problems in power transmission is that high currents have large resistive losses. And with AC current, DC current, you typically have pretty high currents, okay? So you would have large resistive losses. Your generators would have to be very close to where you're using it. Lots and lots of generators, and how you generate that, I don't know. Chemicals are really expensive, but I don't know. But high voltages can be dangerously high different potential differences, okay? Now, there's a lot of people who really worry, I think a little unnecessarily, about the high voltage power lines. Certainly you don't want them falling and hitting you, okay? But those are usually on these huge towers, way away from people, usually not a problem. But I've known people, one of them happened to be a nurse, who was just convinced that her kids were going to be permanently damaged if they lived anywhere close to a high voltage power line, okay? And maybe her kids would, but I don't think most kids would, okay? But that is potentially a problem here. You don't want to mess around with high voltage, okay? So what's the solution here? You can't have high currents without having high losses, but if you have high voltages, which produces low currents, then you have dangerous potential difference. So what they do, they have transformers to boost or lower the currents and voltages in your lines. Now all this comes from this right here, power in and power out. It has to equal power out. And what they've left off here, and I think they maybe show it in another slide or two, but I think it's important to show here. We say, let me get my pen back. Okay. Power in equals power out. Maybe, yeah, I think that's okay to write it this way. What is power, especially electrical power? Do you remember the formula for that? I think we hit it last time, didn't we? Again, I'm teaching 2 courses at the same time, covering almost the same material, but not in the same order. Didn't we talk about electric power before? I've got to go back and see quickly. Yeah, we did. Electrical power and electrical work. Yeah, I know we did. It was equation 6.6. Anyone remember what power is electrically?
Current times resistance.
Say again?
Current times resistance.
Okay. Current is I times R. What's that equal to? That's equal to V. Voltage equals current times resistance. Whose law is that? Ohm's law. So that's Ohm's law. This one looks very similar, but slightly different. What is power? Any guesses? Okay. Let's go back to mechanical power. What was the definition of power? Remember running and walking the stairs. What is power? You just turned in the lab. Okay.
Oh, wait times.
All right. I guess the answer is nobody remembers. Okay. Power is the time rate of change of using energy. Remember, it's the same energy for you to walk up the stairs as to run up the stairs, right? The energy is the same. The work is the same, right? But what's the difference? The time. When you walk up the stairs, you use more time. You don't use as much power. When you run up the stairs, less time, greater power. Remember? Okay? So power was energy per unit time. So I'm going to put energy per time. And that would be in joules per second. Right? Okay. Now, which one of our electrical units deals with energy? Think of the elements in your circuitry. You have a power supply, you might say. You have the resistor or the load. You have the wires that carry the charge. Which of those is supplying energy? Power supply. What do we often call that? In the lab last time we did? Big line, little line? A battery! Exactly. And what does a battery supply? Voltage. There we have it. So someone tell me what a volt is. I almost have given it to you, but I know we did it last time several times. A volt is a joule per energy per unit charge. You're giving those coulombs energy. The amount of energy you give each coulomb, that's it. So that's joules per coulomb. Okay? Now, which of our electrical units deals with time? I'll put it this way. The time rate of moving charge. In other words, coulombs per second. What is that a measure of? A moving charge is called a, whether it's this way or this way. Current. What's the symbol for current? I. And I is equal to Q over time. And that would be coulombs, that's charge per second. Okay? So if V is joules per coulomb, that's what a volt is, and amp is a coulomb per second, what happens if we multiply those two things together? joules per second, which is power, energy per unit time. So guess what power is? Voltage times current. P is equal to VI, IV, it doesn't matter. Most of the time you see this. Power is equal to current times voltage. Okay? In the old days, we used to call voltage electromotive force, and they didn't use V, they used E. The reason they don't use E is because now they use it for energy. But then it was P is equal to IE. I always remember that one because I love pi, so never mind. Okay, but that's beside the point. We use P is equal to IV now. So this means the voltage in times the current in has to equal voltage out times the current out, right? Okay, so that's where you get your power in, power out. Now, I don't know if that's particularly helpful now, but I wanted to remind you of all that at this point. So basically what the transformers do, they either boost or lower either the current or the voltage. It's going to be both. If you're boosting voltage, you got to lower current because that's going to be the same whichever. Okay? The product has to be equal. So if one goes up, the other goes down for the product to be equal. Or if one goes down, the other has to go up. So if you boost the voltage, you lower the current. If you boost the current, you lower the voltage. Okay? So when you have high currents, you have lower voltage. When you have higher voltage, you have lower currents. Okay? Now, so for transmitting long distances, like between the power plant somewhere way up there in northern Jefferson County to us, you want to send high voltages, low currents, because you don't want all that line loss. But when you go to put it in your house, you don't want that high voltage coming in your house. You want low voltage. So you have a transformer there to drop the voltage and raise the current. So the basic thing is power in equals power out. And what you do is change the number of coils, and the number of coils relates to the voltage. Okay? So what a transformer is kind of like an electromagnet. Kind of. You've got an iron core or a ferromagnetic core, okay? And you have so many coils on this side and so many on that side. This is the input side, that's the output side. If you have a huge number of coils here and a small number of coils there, you're dropping the voltage. So you're increasing the current. But if you have a few coils here, large number of coils here, you're boosting the voltage, dropping the current. And this is the equation that relates those together. The voltage on the primary side, I would have called that the inside. So V primary is to the number of coils on the primary side as V secondary is to the number of coils on the secondary side. And there's that transformer hanging outside your house or apartment or wherever you happen to live. I bet you every one of them, if you go home, look around on the power poles, close to the house, you're going to see one of these. Right? Go look. Don't touch it. Don't get close to it. Okay? And that is a step-down transformer. It's coming in with high voltage, not super high, but high voltage. So on this side, you have a large number of coils, and on the other side, you have a small number of coils, so the voltage coming out is much less. Current is going up. You see the current only has to travel from there to your house and then in your house. That's not a lot of line loss. Okay? So you'll be fine. Okay? But going from the power plant to here, that's a long way, so you want the high voltage, low current. Okay? Now, in reality, there's been several of these along the way. Now, have you ever seen, I just drove by one the other day, where was that? A fenced-in area, and it's called a substation. And you have these big coils back there. Those are transformers. So the first substation that's coming from the power plant into a town, usually it's outside the town, you're going to step down the voltage a little bit, stepping up the current. And then you come a little bit closer, and if you're going to have a lot of businesses, but fairly close by. Then you'll have another substation to take it another step down, and then you'll go and do that. So I don't know how many substations you'll have, but typically you have quite a few. Okay? I know at UAB, there's almost a city block. It's all chain link fence, tall chain link fence, and may even have razor wire at the top that they keep people out of there because that's where your transformers are. To run all the hospitals and classroom buildings and libraries and everything else, office buildings. Okay. Oh, let me erase this. I was going to say what happened there. I didn't see anything. Here's what's happening. Here is a simple type deal. 120 volts here with 10 turns here. And you only have one turn there. Your voltage in, 12, over the number of turns, 10. Okay? As to voltage out, we don't know what that's going to be, but only one turn out. Okay? Well, if 12 is to 10, as V is to 1, if this reduces by a factor of 10, this will be a factor of 10. 120 reduced that by a factor of 10, you got 12 volts out. Right? That's a step-down transformer. Now, I don't know if y'all have run into this before, but several years ago, my wife decided she wanted night lights around the house. It's just too dark and scary. She wanted lights to come on at night. And we checked out at Home Depot and found a low-voltage nightlight system. Okay? And it had a transformer. It was in a little metal box, and it hummed a lot, okay, when it was plugged in. But it stepped down the household voltage, or 120, to, I think, either 6 or 8 volts. It seems like it was 6 volts. And then the lights ran on 6 volts. And you had the lights for the steps going up to the front door, lights on the trees or the windows and things like this, you know, all based in the ground. And we ran the things in pretty simple installation. Over the years, some of them went out and they were hard to replace and stuff, so she hired someone to do the next one. And so far they're doing okay. Okay? That was a step-down transformer going from 120 to 12. So that ratio was 20 to 1. I mean 120 to 6. That would have been a 20 to 1 ratio, of course. On the other hand, if you had 120 volts here and only had one turn here, no, you never just had one turn, and you had 10 turns over here, what have you done to the voltage? Stepped it up by a factor of 10. So now you have 1,200 volts or 1,200 volts. Better be careful with that, okay? You won't have much line loss, but you could really do some shocking and stuff with that. Okay. Make sense? All right. Now, next part that here we go. We finally have an example. Example 6.9. Let's go back here. I don't have much room to write here, so I guess I'll write it in that little space there. A step-up transformer has 5 loops in the primary coil. Now, in that formula, what would that be represented by? What symbol? In that formula down in the corner.
Yeah.
That's N sub which? Primary? N sub P. And that was 5. 5 loops on the primary coil. And 20 loops on the secondary coil. What would that be? N sub S is 20. Okay? Loops. Secondary coil. If the primary coil is supplied with an alternating current of at 120 volts, what would that be? V sub P would be 120 volts. That's normal household current. Voltage. What is the voltage in the secondary coil? So what we're looking for is VS, and that's the unknown. Any ideas? Second? I can't hear. Proportion? Yeah, set up your proportion. So we have V sub P, and it doesn't matter which way you set it up. I'll do it the way they did. V sub P over N sub P, that would be 120 volts over 5 as V sub S, that's what we're looking for, is to 20. And how do you solve that proportion? Okay. Actually, say again. Oh, multiply. Okay, what were you saying? Okay. Since the 5 is multiplied by 4 to get 20, multiply the 120 by 4, and what do you get? 480. You're absolutely right. That's the easy way to do it. Okay? The other way to do it, generally for a proportion, is you do what you call cross multiplying. 5 times Vs is equal to 120 times 20. Cross multiply. And then multiply those two together, divide by the 5, and you'll get 480. Yeah. But the way you said it is the easier way. If that's a simple multiple, just multiply it there too. And sure enough, that's what they get. They do it the long way, but they still get 480 volts. Okay, that was example 6.9. Let's do 6.10. The step-up transformer in this one is stepped up the voltage, is supplied with an alternating current of 120 volts. So your I in, which is I'll call IP, is, what did I say it was? Wait, supplied with alternating current at 120 volts and a current, that's a weird way to say it, okay? Alternating voltage of 120 volts and a current of 10 amps, 10.0 amps, okay? It says now, what is the current flow in the secondary? So what is your I sub S? There's your unknown now. How in the world are you going to do that? Any ideas? Help me, folks. Don't leave me hanging. What's your underlying basic relationship? Next to the bottom line on this side. Oh, power in equal power out. Okay, let's do that one. Except we'll call it, because they aren't using in and out, power on the primary side is equal to the power on the secondary side. So we'll use P and S rather than in and out. Okay? And what is your power on the primary side? What do we say power was?
120.
Say again?
120.
Okay. Tell me what power is in terms of these things over here. 120 is part of it, but not all of it. See, we like to call power voltage. Don't get that confused. Power is not voltage. What was our formula we had just a little bit earlier? Power is equal to? Talked about it in high voltage power lines.
Oh, I times V.
Say again?
I times V.
I times V, exactly. So this will be IP times VP, very important person, okay, equal IS times VS. Power is I times V, current times voltage. And what was your IP over here? 10 amps times, what was your voltage on the input side, primary side? 120 volts is equal to, what was the, this is what we're looking for, IS, we don't know. And what was your voltage on the secondary side? You told me. Second? You were the one who gave me the answer. 480, is that what you said? Yeah, 480 volts. Okay, that's how you determine what the current is. Okay, you can multiply these two together, divide by that. So I'll do it here. I sub S is equal to, I can't read my writing. I think that's the product of these two is 1200, right? Divided by the 480. Okay? Pull out your calculator, see what you get. 1200 divided by 480. Okay, I'll buy that. 2 point what? 5. And I is measured in? I is measured in amps. I'd say 2.50 because I think, no, maybe not. The N was only 5. See which they, no, they just used 2.5. I was happy with that too, but I changed my mind thinking they were going to do that. 2.5 amps. Which, by the way, just like you did this, multiply by that factor of 4 because you had it here. Since the current goes down when the voltage goes up, and we did have voltage going up, then divide the current by 4, and 10 divided by 4 is 2.5, right? So you could have done it easily that way if you saw that. But this way works too. Any questions on that? That's 6.10, 2.5 amps. All right. Now, there is a little blurb on page 165 let's talk about before we get started on current connections. And I don't know if you've ever seen this as an apparatus or not. But what you have here, hanging on one bar here, is a coil of wire. Okay? Hanging on another bar is another coil of wire. Okay? You place this coil of wire over a strong permanent magnet here. Okay? And put this one over a strong permanent magnet. Now notice there's no battery, no power supply, nothing's plugged in, just a coil of wire hanging over a battery, coil of wire hanging over a battery. Right? Just sitting there. Start rocking this coil of wire. What happens? Oh, the wires are connected. I forgot to say that. The wires are connected. Start rocking that coil of wire, and what happens? This coil starts rocking. Why? Because when you rock the coil, you're cutting the number of field lines coming over the strong magnet here, changing the number of field lines being cut by rocking the thing, by the number of coils that are there. That induces a current in this coil that's connected to this coil. The current flows through here. The current now is sort of like you made a generator here and made a motor over here. It starts moving because the changing current induces a magnetic field that swings over the magnet here. It's pretty incredible to look at. You start this moving, this and start moving on its own. This becomes a motor, generator, this becomes a motor, okay? Pretty strange, but true. And they're identical, except reversed. Okay. So, current connections. This is, 6.6, which I think may be the last section in the chapter. Okay, let's see if we can finish it. Current connections. Just about all household current is alternating current. Okay? Practically all generated electricity, if it's made by a generator somewhere out there, even in your car, that's alternating current. Practically all generated electricity is alternating current. Now, that's usually what we transmit over high voltage lines. We do the high voltage to cut down on. By the way, at the generating stations, I think somewhere in your book, either we've already seen it, no, we're going to see it on the next page. At that generating plant, the hydroelectric dam, the steam power plant, whatever it is, you'll see these great big old transformers that are step-up transformers. Whatever that's producing, they step up to a very high voltage, so they transmit that over high voltage lines. These are these huge power lines that you'll see cutting through the woods and stuff like that. In fact, down on the farm in Georgia, I don't know if any of you ever heard of Plant Vogel. It was a nuclear power plant on the Savannah River, south of Augusta, Georgia. In my home county, Burke County, at Shell Bluff, or somewhere pretty close to Shell Bluff, and it was had 2 reactors, I think, and just it's been the first new reactor activated since 3 Mile Island, which was a generation ago. But they finally have started doing new, and I think there's been another 1 or 2 since that. But anyway, they have already cut huge swaths of these high-powered, high-voltage lines, cutting across the farmland, the woods, and everything else to get that power probably toward Atlanta. You know, that's going to be the big source of it, but it's going to be farmed out on the way. Okay? So that's transmitted over high-voltage lines, step down to come into your homes or even into your cities or industry. Now, industry may not have to step down as much as home does. Depending on what your plant is doing, it may require 360 or 480 volts rather than 120, but whatever it's doing. On the other hand, your direct current is used in automobiles. Even though you generate, you do another. Now, they're often called these things transformer too, AC to DC transformer. Yeah, that is a transformer, but it's not the same as a voltage transformer. Okay? Cell phones, MP3, laptops, computers, all this kind of stuff. Anything that uses a battery is going to be direct current. Movable and portable applications, the main current source is chemical batteries or some type of battery. So it was sort of natural that an automobile could be done electrically, but of course with DC, battery. Okay, sure, they plug it into AC outlet to charge the battery, but guess what? You have to have something like a dual diode transformer to change that AC to DC to charge the batteries. Okay, but the main source is usually your chemical batteries. Okay. Now, voltage sources in circuits. Okay. Now, this is what we sort of did in the first lab, the one we did last time. I wish we hadn't had to do the lab before we got to this portion of it. We had talked about the circuits, but not these kinds of things. There are 2 ways we talk about things in series. And we sort of did this in lab, but not directly, but you caught on to it pretty well. In a series circuit, whatever you're doing in series, the same current flows through everything. Here we've got our batteries in series. So minus goes to plus, to minus to plus, to minus to plus, and to your source. What does that do for you? Let's say each of these dry cell batteries is, say, a 1.5 volt battery. What is this doing for you?
More voltage.
Say again?
More voltage?
Yes, you've increased the voltage. If each one of these was 1.5, from here to here is 4.5. 3 times 1.5 is 4.5. So you have more voltage. The same current flows through everything. Okay? But the voltage is increased. Okay? Well, right. Let me take that back. The same current flows through the whole thing, but with more voltage, it becomes more current because the resistance is the same, right? So therefore, you have 1 cell, you have a dim bulb. 2 cells, you have a brighter bulb. 3 cells, you have a very bright bulb. And y'all did that in lab too, remember? As you increase the voltage, you increase the brightness, because with the same resistance, increase the voltage to 4.5 or something like that, you triple the current as well. Higher current makes a brighter bulb. Okay? But for any given circuit, the same current goes through each battery. Okay? Total voltage is the sum of the single cell voltage. That's a single current pathway. That's what I was trying to say. I hope it came across. Okay? Now, what if you put your batteries in, this is called parallel, plus to plus to plus, minus to minus to minus. Okay? Now, in this setup, what does your voltage do? You have, say, 1.5 across this one, 1.5 across this one, 1.5 across this one. What you have across here? 1.5. You haven't upped the voltage at all. Okay? If you only have 1.5 volts, then the light's going to be that dim light. because it's only going to provide a certain amount of current. So what in the world advantage would you have in putting it in parallel? Say again? Okay, I think you just hit it. Okay, I didn't quite understand what I think you did. What if you had a remote weather station or something like this, way up on top of Mount Shiha or something like that? And you didn't have power going up to it, so it was all being run on battery. And so every couple of months, the battery's going to run down. You got to climb the mountain and go up there and change batteries. Guess what I'm going to want to do? And it all runs on the same voltage. I'm going to put a bunch of batteries in parallel, and now they'll last 3 times as long because they're not supplying. Each one is only supplying so much amperage, and that will keep it going 3 times. So now rather than every 2 months, I only have to go up there every 6 months and climb the mountain and change the batteries. So I might even put more in parallel. That's what happens when you put them. All the negative terminals are connected, all the positive terminals are connected. Resultant voltage is determined by the largest single cell battery. So if this was a 1.5, a 2, and a 1.5, then the voltage would be a 2. Okay? This one will supply a little bit more, the other would boost a little bit. Okay? It makes a greater electrical energy available, so it would last longer. It lengthens the lifetime. That's what parallel power sources do for you. But most of the time we're more interested in resistances in the circuits. Okay? This kind of resistance, here we have your power supply. If this is a 1.5 volt battery or whatever, okay, and you have one lamp, another lamp, and another lamp. Now, right now we'll assume all 3 lamps are equal. Okay? Now they like to draw the electron current. The conventional current goes in the opposite direction, of course. Okay? What can you tell me about those lamps?
All sharing one.
That what?
They all sharing one.
Yeah, they're all running on the same battery, you're right. And just like before, the same current is flowing through each one of them. So how does that compare if you only had 2 bulbs, or even if you only had 1 bulb? What would happen to the brightness of the lamps? Say again?
Right.
Which one? The 1 or the 3?
One.
The 1, for sure, absolutely. Because what you've done here with the same voltage, you've tripled the resistance. So if you triple the resistance, you have reduced the current. Because the same voltage is here, and V is equal to I times R. If you triple the resistance, you have to have a third the current. A third the current is going to be really dim bulbs. Okay? So, that's what having tripling resistance. The total resistance is the sum of each component. If they were different resistances, you just add them up. Okay? The current drops as more elements are added because you only have the same power supply, the same voltage supply, energy supply. So the current has to drop because the same current flows through each. And what happens if I remove a bulb?
They all go out.
They all go out because you've broken the circuit. Okay? Do y'all remember the old Christmas tree lights? The old Christmas tree lights? That if one bulb went out, the whole string went out. Y'all ever have any of those? I bet you your dad hated those. I know mine had to go in and one at a time replace each bulb, and finally, hopefully one would come on. And if it didn't, that meant 2 went out at the same time, so then he'd have to do it. He was not a happy camper. Okay? All right. Total resistance is the sum of the components. The current drops, the more elements are added. Because you've got the same voltage, more resistance, the current has to drop. Okay. So your effective resistance, or the total resistance, is R1 plus R2 plus R3, as many resistors as you have in that series circuit, where everything's connected, plus to minus, all the way around. And by the way, your current, your voltage is divided here, they say. you only have a certain voltage drop here because you have that new current times this resistance. That's the voltage drop across this one, plus the voltage drop across this one, plus the voltage drop across this one. That has to equal the total. So each one of these, the voltage drop across these, is less than the voltage drop across the battery because the voltages add too. The current's the same in all, the current resistances add, and the voltage drops have to equal that. So the sum of the voltage drops equals that. Okay. So the resistances add, as do the voltage drops. Okay. Now what do we mean by parallel connection of resistance? Okay. Well, here's what it looks like. Here's your battery, the dry cell battery, let's say 1.5 volts. And here we have three, let's call them equal now, bulbs just like we had before. 1.5 volts across here, coming in, going out. What's the voltage drop across this one? 1.5, because this is connected to the 1.5 side, this is connected to the 1.5 side. Okay? This is 1.5. This is 1.5. So each one of these draws the same amount, has the same voltage, same resistance, same current. But the current, part of the current goes here, part goes here, the other part goes here. So now the current's not the same. The voltage is the same across all three, rather than being split between the three. But the current is the same. The voltage is the same, and the current that comes out of the battery and into the battery has to equal to the sum of those three. So you have more than one current path available. The overall resistance with three bulbs here, do you think it goes up or goes down? Overall resistance. You would think it would go up, wouldn't you? It goes down. Because what is resistance? Voltage divided by current. Voltage divided by current. So you have the same volt here, but you now tripled the current. So you have a greater current. Same voltage divided by a larger denominator makes a smaller resistance. So the overall resistance of this system is less than the resistance of 2, which is less than the resistance of 1. It doesn't seem to make sense, but it's true. Okay? So the overall resistance drops as more elements are added. Whoa, that doesn't sound safe, does it? Because as resistance drops, the reason it dropped, the current's going up. And soon, you're draining this battery like crazy. Okay? And so it's not resistance that drains the battery, it's current that drains the battery. Okay? If you're on a 120 volt system that you can't drain the 100 system, you just get more and more and more current. After a while, you're burning the wires. Unless you have a fuse or a circuit breaker. I'm surprised anyone remembers what a fuse is. Okay, but yeah, a fuse or a circuit breaker. Okay? And that keeps the circuit from overheating. So the total current increases as more and more elements are added. That drops the resistance, and it increases the chances of overheating. Okay, now you can't see it. Let's see if we can remove that. There it goes. Here's how those resistances work. Now it's an inverse relationship. 1 over your R total, I like to call this R effective. Okay, effective resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Because guess what happens? As you keep adding resistors, you're adding reciprocal forms. This gets to be smaller and smaller. Okay, no. You're gradually increasing the sum here, but by a reciprocal amount. So this does get bigger, but then this is reciprocal itself. So as this gets bigger, this thing gets smaller. So the overall resistance is getting smaller. The effective resistance is getting smaller. Okay? Now, yuck. We've run out of time. Sorry, folks. I'd hoped to finish the chapter. On page 166, a neat picture, looks like a hydroelectric dam, and look at the size of those step-up transformers. I think that's what they are. Huge things, really bumping up that voltage. See the power lines going out. They're going miles and miles to get to the cities where they're going to be using that power. Whereas there's the one we saw in the earlier picture outside your house, that's a step-down transformer. We have lab. Yeah.
Yeah, I got it.
Okay. All right. Okay. There is a little blurb, Science and Society, at the top of the page. I don't know, were any of you born in 2003? I bet not, right? No. Back in August of 2003, some problems with a huge electrical grid resulted in power plants throughout the Ohio Valley, the Northeast, all over the place, blacked out. All of the Northeast, the big, power-hungry part of the country, went black. I mean, for days. And there's several things you can read on that. Pretty interesting. So we will start next time with example 611 on page 167. We have very little left to do in the chapter. We'll do those two examples. There's a closer look here. And then we're on household circuits now, so we'll pick up there, and that will be it for the chapter. So, what this means for us, today we'll do the lab on Ohm's Law. It shouldn't take too long. I've got to set it up because I didn't have time because of L Day. I didn't get a chance to set up the lab. So I might ask a few able-bodied people to help. So we'll set up and do the lab. Then we'll be through for this week. Tuesday, it won't take us more than 15-30 minutes to finish the chapter. Okay? And then we'll get started in chapter 8. All right? Then at the 2 hours before the end of the chapter, end of the time, we'll do the last chapter on electromagnetism. Okay? Then on Thursday of next week, we will continue in chapter 8. And whether we have time for the lab, that depends on whether we have time to finish the chapter or not. But we'll definitely have the test the last 30 minutes. The test on chapter 6, last 30 minutes on Thursday. And then the Tuesday of next week, we'll finish up chapter 8, finish the lab of chapter 8. I'll return every test and lab to you that I have. And so be sure to get everything in by Tuesday. If it's not in by Tuesday, if this is not this coming Tuesday, the following Tuesday, you're getting a 0 on that. Okay, so please get everything finished next week so I can return everything to you before then. All right? And then on Thursday, we'll have the final exam.
What number room is it?
What's that?
What room number is it?
What room number what?
Or where's your room at again?
Oh, my room, my office, 265.
265?
Okay, go down this half flight of stairs, go almost all the way to the end of the hall. Before you run into the wall, there's a stairwell, but just this side of the stairwell between the mechanical room and stairwell, that's my office there, right across from the orientation classroom. Okay? Okay. So, lab today, finish chapter 6 on Tuesday, have the last lab on chapter 6 on Tuesday, maybe finish, I think we'll finish chapter 8 on Thursday. Probably have, well, if we don't finish, we'll continue that. And then the following Tuesday, we'll probably have the lab and then have the final exam. We'll have the test on chapter 8 and the test on final exam, comprehensive. And the test for this chapter will be next Thursday because we didn't finish the chapter today. All right. Let me see. Do I have the labs? I went down to get the labs and it was locked up and I couldn't get in. So I had the labs run off, but I asked one of them to put them in my box. They didn't put them in my box. The office was locked. I couldn't get to them. So I have to go get the labs, and I also have to set up the equipment. So go down here to the same lab, 253. I'll be there fairly shortly. I might need some help getting equipment up. Okay? I'm going to pause this. All right, we're recording again, doing lab on Ohm's Law. I can't remember which number lab this is, but whichever one it is. I know you've read the first page page 193, they tell you about electrical potential difference between 2 points is measured by the potential difference. What do we use to measure potential difference? Volts. Very good. And what does a volt stand for? What's the fundamental unit? It's not really fundamental, but more basic units. Joule per Coulomb. Exactly. Very good. Okay? And then we also will be measuring current. And by the way, your power supply here will be measuring the voltage, just like it was last time. What is current? Amps. That's the unit for it. What does it measure? Of what? It is a flow rate of what? Your charges. And what's the units for charges? Coulombs per second. You got it. Flow rate, time rate of change of of charge. And we'll be calculating resistance by Ohm's law. Okay? How does that go? And what unit do we use to measure resistance? Ohm. Okay? What symbol for that? Units? Units are? The symbol for the unit? The capital omega. Perfect. Okay? And how do we do Ohm's law? This has three manifestations. What are they? Okay? Or? Okay, good. Something like that. Okay. So we got those. All right. Now, if you'll notice here on page 2, known resistance, I put a resistor in, and you'll see you have an adjustable power supply, ammeter connected to that before it goes to the resistor. The voltmeter that you show here, we're actually using in the power supply. Okay? So we don't have to have a separate voltmeter. Okay? And what it says to do, you will adjust the DC adjustable power supply as instructed by your laboratory instructor. That's me. Okay? Obtaining 6 values for voltage and current. Voltage you'll measure off the power supply, the bottom box. The current you'll measure off the digital ammeter on top. Okay? I'll set that up again for you in a minute. Let me tell you what to use as your volts. If you'll turn to the table on page 197, this is for your first resistor. Okay? It says known resistor. I'll tell you what it is in a minute. Trial 1, I would suggest volt 1. Now, you might not be able to get it sit right on 1, but as close as you can. 0.9, 1.1, 0.8, 1.2, whatever you can, as close as you get to 1 volt. Then trial 2, 2 volts. Trial 3, 3 volts. Trial 4, don't write them in yet because you'll write in whatever you get it to settle out at. Then you'll measure resistance. Now it says here, measure it in amps. Okay, record it in amps. What you're going to be measuring it in is milliamps. Okay? Because you'll see the scale I put it on is going to be milliamp scale. So you'll have to read that off the scale and change it to amps. How will you get milliamps to amps? Move how many places? 3, you said? 3, okay? And you move it to the left because you're going from a small unit to a big unit, so you're going from a big number to a smaller number, so you move it to the left, okay? 3 places. So whatever you read on your scale, move 3 places to the left. That will be the amps that you record. Everybody ready to roll? Okay. Now I'm going to set it on the 200 milliamp scale. That may not be good enough to begin with, but see what you can get. Good deal. And here too. If you run this battery down already. Okay. If that doesn't work, you can move it up to the next scale. Okay? Now, remember the red buttons are on off, and your toggle over here adjusts the variable voltage. So press that in. Okay? Pressure to get as close as you can to 1.0 volts.
Touch it.
Okay. And And Travis got the winner again, huh?
Yeah. I'm pretty good at figuring it
Okay. Yeah, I'm sorry about that. So y'all set your voltages, record those, and read your amperage, but be sure you change your amps from milliamps to amps. Okay? And while y'all are doing that, I will set up the next part. I'll get ready for the next part. Yes. Okay. Yeah, if you can't get that, scale it down one. Woo! There you go. Might have to go two. So that would be how many milliamps to two places that way. Yeah. Again, check this and make sure this and that match up. 0.9 volts, and that looks like about 7.8 milliamps, which you move three places to get amps.
Cranking it up.
Yeah, this was the whole scale here, right? Got 20 milliamps, that was 2,000 microamps. So what you're reading is milliamps. Y'all got one, y'all got one. Y'all got one. Okay, if you're running into any problems, please ask, don't assume.
Don't touch it.
All right. There it is. Oh, I'm going to turn off now. Okay, back on page 194, you will obtain DC power supply as blah, 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 blah. Adjust it as instructed, set up the circuit with the power off, do not, blah, blah. Record the value resistor and the 6 values of the current in data table 22.1. I hope you put it in the right table. Okay? Now, I will tell you now, as some of you were looking, the resistor that said was a known resistor is 100 ohms. Okay? But don't let that distort or color your calculations. We'll be doing those later. I'm going to replace those with another resistor. Okay? and you'll do the same type of procedure with this one. What you'll find, you use the same voltages you did before, but of course you'll measure different currents.
Whatever you have to measure, that's what you measure.
Okay. I thought you were reading the numbers on the color band, but you were. Okay. All right, so start doing your measurements here. Do just like before, 6 data points. Try to aim for 1, 2, 3, 4, 5, and 6 volts. Reading your current, but matching your voltage to your current. Make sure. Oh, and now your currents are probably going to be less, so be sure you change the milliamp reading that you read to amps, which is what you record. Okay? Any questions?
What's the resistance you put in?
What's that?
The resistance you put in.
The first one that you had was 100 ohms. This one you're going to calculate and tell me what it is. Okay? So we're not going to do that yet. Okay? So, yeah. Be sure you match up. If you have any questions, please ask. Y'all going okay? Okay. Repeat with the unknown resistor. Okay? Record your data table 22.2, which I hope you did. All right, here's for the results. Make a graph of the 6 data points of data table 22.1, placing the current on the horizontal axis and the voltage on the vertical axis. Okay? Now, I want some of you to give me your range of currents. I have a feeling, voltages. They're going to be basically 1 to 6, right? What's your currents, approximately? Just from what? On the first table, 22.1. .060? 0.06. Okay? Okay. So basically, you've got about the same range. Okay? So it doesn't matter whether you do landscape or portrait on that first one. The second one, it might matter. Give me on your next table is again 1 to 6 on the voltages. What are they on the currents?
0.002 to
0.16. Okay. Your other one went to around 6. Okay. So on that table, I think your voltage, okay. On both of these, I think it'll be safe to go current on the horizontal scale and voltage on the vertical scale like that. Okay. I think that'll be safe on either one of those. Now, again, your voltages are 0, 1, 2, 3, 4, 5, and 6. You won't use the top 3. And then your bottom scale, it sounded like 0.1, 0.2, 0.3, no, 0.0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, approximately, right? That will cover your first one. Okay. So 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. If you have a few more one way or another, you got plenty of room to put those in. Okay? So, as I was saying then, with the current in the horizontal axis, when you go portrait mode, and the voltage in the vertical axis, plot your points. Each team has some rulers. And y'all came over to my table, left your rulers back at that table. That's fine. You can go get them. Oh, yeah. And draw the best straight line that you can through the 6 data points. Now, that doesn't mean wiggle the line to touch them all. That means use the ruler so you minimize the error, that you can, as much as you can, draw the best straight line that you can through those 6 data points. If using 0, 0 will help, that will be okay too, because if you had 0 volts, you'd have 0 current. But if 0, 0 doesn't help you, then use the 6 points you do have. Okay? So once you have drawn your line with your ruler, not by hand, with your ruler, and then calculate the slope. And we know how to do that, don't we?
You're going to have to reteach me on that one.
Say again? Okay. Draw it and get it done, and draw your line, then we'll talk about the slope.
Yeah.
Okay?
You gotta use slope-intercept form, right?
What's that?
Slope-intercept form?
No, you'll just use the slope.
Slope.
And you'll use V2 over V1 V2 minus V1 over I2 minus I1. Vertical, change your vertical over change your horizontal. Okay. As soon as you reach an impasse or reach an answer, either one, let me know.
Yep. Something like that. Not right there.
Oh, yeah.
I mean, it wasn't too bad. Yeah. For a jumpy hole maker, power supply.
Oh, yeah.
It's 2.9, and then right in the middle between 2 and 3.
Oh, yeah.
Yeah, exactly. Okay. I take it a few people have finished the first. Let me turn on the projector again. I mean my recorder. Oh, I just did the wrong. No. Okay, all 3 teams have calculated the slope, and I hope they wrote that somewhere under number 1 on page 194, and also somewhere on the graph on that first page that doesn't have a number on it. Okay? Now, number 2 on page 194 says, compare the calculated value of the known resistor, and I told you what it was, right? What? 100. With the accepted value as given by your instructor. Okay? Your calculated value is one you just calculated. I think you had 98, you had 101, you had 89, right? Okay? So, I'm going to say that I had, which I didn't do it, I had 103, no, how about 111? Okay? That's what I measured. Okay? I know the real was 100. So I take the difference of those two, measured minus calculated. Okay? For me, that's 11. And I divide that by the actual. Okay? Measured minus actual. Actual is 100, so my error was 11%, because 100 is your denominator. One of you had 1%, one of you had minus 2%, and one of you had, I think, 11%, minus 11%. Right? That's how you do percentage error. It's the measured minus actual. Take that difference, divide by the actual. Okay? And make it into a percent. Okay? Good deal. All those were good, because anything within 15% with this old equipment, that's pretty good. Now, all of you were well within that. Okay. Even the jumpy one. Okay. So, what you do now, calculate percent error, write that on page 194. Make a second graph, this time of the 6 data points from table 22.2, again placing the current on the horizontal axis, the voltage on the vertical axis. Calculate the slope and write it on page 195 under 3 and somewhere on the graph. So on the second graph, do the same thing. You've plotted your points from your second data table. Make your best straight line, one single straight line, okay? Pick 2 points near the ends and calculate a slope from there and write that on those 2 pages. Okay? When you get that done, you already done it? Okay? I'm going to turn. Okay. So far we've done 3 on the top of page 195. On the second graph, this time you did the 6 data point, blah, 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 write the slope, both in number 3 on page 195 and on the second graph. What is the value of the unknown resistor? Okay, I told you 390 ohms. You had your slope there. Explain how the 2 graphs demonstrate Ohm's law. To resistance, is that what you're saying? And how are they related?
Because as current...
No, resistance is?
What's the formula?
You tell me.
Resistance is because R equals...
It's on yours too. Look at the first page of your lab. Look on the first page of your lab. Lazy bones. Current. And your voltage was your vertical scale? Your current was your horizontal scale? Yeah. Rise over run was measuring exactly that.
Current and voltage are related to Ohms.
Yeah, they're first cousins, aren't they? Okay.
Yeah.
Okay.
Yeah,
Okay. Question, was the purpose of the lab accomplished? You have to answer that however you wish.
yes.
Make sure all the blanks are filled in on everything. And when you're through, you may turn it in to me. Okay? Any questions before I turn off the the recorder? Any questions? Y'all doing okay? Okay, I'm going to go and shut it down then.